We're going to skip ahead a little bit to Chapter 11. We're going to cover the first part of Chapter 11, and we'll cover the second part in Physics 1104. But for now, let's cover simple harmonic motion. So we covered masses on springs, and we also covered pendula a little bit back a couple of chapters ago when we talked about free body diagrams and forces and energy. But now we want to delve a little bit deeper into that subject and describe their motion in more depth. So, let me define simple harmonic motion first. If an object vibrates or oscillates back and forth, traversing the same path, each cycle taking the same amount of time, then we call that periodic motion. And the mass and spring system is a very useful model for a periodic system. But of course, there's a lot more systems that exhibit simple harmonic motion than just masses on springs. Let's assume for now that the surface is frictionless, and there's a point where the spring isn't stretched or compressed, of course, and that is the equilibrium position. We're going to measure the displacement from that point. So this is going to bob back and forth about the equilibrium position, and we'll measure that displacement from equilibrium. We'll call it x, okay? Now, we covered what the force was for this kind of system a few chapters ago, and it's given by Hooke's law. Hooke's law says that the force on a mass on a spring is equal to minus k times x, where k is the spring constant, which is the stiffness of the spring, x is the displacement from equilibrium, and then of course you can always set any force equal to Newton's second law, F is equal to ma. So we have F is equal to minus kx is equal to the mass times the acceleration. Now, it's not so much that masses on springs are in and of themselves that important. It is simply, though, that they are very good model systems for a lot of other things. One example of this would be an Einstein solid. So we model oftentimes the bonds between atoms in lattices as springs. And then the atoms themselves, due to their temperature, will oscillate back and forth, but always about their equilibrium position within the lattice. And this model gets used in quantum mechanics to model solids. It gets used all over the place. And you talk about the stiffness of the bond and model that as sort of an effective spring constant. So there's other systems that are also exhibit simple harmonic motion, but that's one of them. And because there are so many systems that exhibit this kind of motion, masses on springs kind of taken on a really important place in physics. We're going to call any vibrating system where the restoring force is proportional to the negative of the displacement. We're going to call that simple harmonic motion and call this system the simple harmonic oscillator. Now, F is equal to minus kx. The minus sign on the force, and because it's on the force on the acceleration, indicates that it's a restoring force. The direction of it always restores that mass back to the equilibrium position. So the direction is opposite to the direction of the displacement. K, yet again, is the spring constant, and the SI units of spring constant are going to be newtons per meter. The force is not constant, and so the acceleration isn't constant either. The acceleration is minus k over m times x. Since the acceleration is proportional to the displacement, we can see that it's not constant, and we know that we can't use those kinematics equations to describe the motion of the object. We're going to have to do something else. Now, let's define our terms before we jump into the equations. The displacement is measured from the equilibrium point. We're going to call that x. It's going to have a maximum displacement, so there'll be turnaround points where it goes back and goes the other way. The distance from the equilibrium point to the turnaround point will be the amplitude, a. The cycle, one cycle, is defined as starting at a place and going back to that place. In the images here on the right, you can see that it starts at minus a, so this is to the left of the equilibrium position at the maximum compression of the spring. It goes through equilibrium to the max position at the right, back through equilibrium, and then finally back to the left-hand side. That's one full cycle of motion. We're going to call the period the time required to complete one full cycle of motion, and that will be indicated by a capital T. And then the frequency is the number of oscillations or cycles that are completed per second, and the frequency is equal to 1 over the period. Now, contrary to a lot of students' intuition, the period and the frequency of oscillation are not related to the amplitude of the oscillation. Kind of strange, but true. So in the same system, no matter how far you compress or stretch the spring, then that doesn't change the period of the motion unless you exceed the limits of the spring. Instead, the frequency and the period are dictated by the mass and the spring constant. Okay? Stiffer springs have larger values of K, and so they have shorter periods and higher frequencies. And more massive objects that are attached to the spring make the motion slower, more sluggish, with longer periods and smaller frequencies. That's given mathematically by the period t is equal to 2 pi times the square root of m over k, and the frequency is equal to 1 over the period, which is equal to 1 over 2 pi times the square root of k over n. Now, we can find the period as a function of time and the position as a function of time. For this simple system, the motion is just a sinusoidal function because it's periodic. Okay? So, let's define the angular frequency, omega, as 2 pi f. And let's set the motion, x, equal to a, the amplitude, times the cosine of omega times t. You can sub in for the value of omega if you want to, and you could write x is equal to a cosine of 2 pi times f times t, or a is the cosine of 2 pi times the time divided by the period. Okay, so any one of those functions will be just fine. So this is sinusoidal. It's described by a cosine function. So I have a simple example that I want to show you that illustrates everything that I've got here. So this is a little program, little code, and I'll post it online so that you can play with it too. Okay, so let me set this and start it. If I have a kind of medium range value of my spring constant, I'm going to set my spring constant equal to 1, and I'm going to have my initial position maxed out there, and I'll set it. So what's going to happen now is I'm going to start it and we'll watch the system go. And you can see that the motion is indeed sinusoidal, and it looks like a little cosine function there. Okay. Now another thing is you can see that the displacement, when it's to the right, the arrow points to the left, and when the mass is to the left, the arrow points to the right. It's always pointing back at that equilibrium position. Okay, now let me play with the spring constant a little bit, and we'll see why the period is so dependent upon the spring constant but not necessarily upon the amplitude of oscillation. So if I increase my spring constant and make it a factor of 2 larger than it was before, watch what happens to that force arrow. Remember, F is equal to minus kx, so as I increase my spring constant, my force gets larger too. And when my force is larger, that makes my acceleration larger as well. So you can see now that when I let it go, the motion is much faster than before because the force and the acceleration are so much larger than they were before. Okay? So it's going faster. But you can see that it's not dependent on the amplitude of oscillation. Here I haven't changed the amplitude of oscillation at all, and yet the period is a lot shorter than it was before. Okay? And I encourage you to play with this on your own so that you can see it for yourself. Let me do an example problem for you. So here we have a 200-gram block connected to a light spring with a spring constant of 5 newtons per meter, free to oscillate on a frictionless surface. The block is displaced 5 centimeters from equilibrium and released from rest at t is equal to 0. So find the period and write the expression for x of t. Okay, so omega is equal to 2 pi f, and f is equal to 1 over 2 pi root k over m. So this 2 pi cancels out, and I get omega, which is what I need to put into my cosine function. Omega is equal to the square root of k over m. So when I solve using my numbers in this problem, omega is equal to the square root of 5 divided by 0.2, which gives me omega, an angular frequency, of 5 inverse seconds. Now the period is what it asked for in the problem, and the period is equal to 2 pi over omega, which is 2 pi over 5, which gives me a period of 1.26 seconds. The problem says that the block is displaced 5 centimeters from equilibrium and released from rest. If you pull it back and release it from rest, that means that you've given it its maximum amplitude. Okay? So the amplitude will be equal to 0.05 meters. So now when I plug in x is equal to a times cosine omega t, and that gives me x of t is equal to 0.05 meters times the cosine of 5 inverse seconds times my time t. Okay, Simple harmonic motion, if you hang the spring vertically, it doesn't change too much. But if you just have a free spring and then you hang a mass on it, the spring will then stretch down a little bit due to the force of gravity on that mass. At the point where it comes to equilibrium, then you're going to have the force of gravity acting downwards and the force from the spring acting upwards. Those forces will be equal in magnitude but opposite in direction as long as the mass isn't bobbing back and forth, okay? And the net force is zero. So at that point, you can see here in my little free body diagram, I've got my pink arrow up indicating the spring force, but it's the same length as the pink arrow that points down, which is gravity. So mg is equal to kx at that point. Let me do an example problem for you with a vertical spring. A spring is hanging from the ceiling. Attaching a 500-gram physics book to the spring causes it to stretch 20 centimeters in order to come to equilibrium. What is the spring constant? And from its equilibrium position, the book is pulled down then 10 centimeters and released from rest. So what's the period of oscillation? So I'm going to set kx equal to mg and then solve for k to find my spring constant. Solving for k gives me mg over x. Plugging in for the numbers that I've got in this problem, that gives me 0.5 kilograms times the acceleration due to gravity of 9.8 meters per second squared, divided by 20 centimeters put in terms of SI units is 0.2 meters. So when I solve that equation, I get 24.5 newtons per meter for my spring constant. Now for my period, I've got the equation t is equal to 2 pi times the square root of m over k. Plugging in the numbers for m and k that I found in the previous step, I get 2 pi times the square root of 0.5 divided by 24.5, and that gives me a period of 0.9 seconds. So it's pretty straightforward. Now, a few chapters ago, we covered the potential energy of a spring system. Remember that we had two kinds of potential energy that we were covering in previous chapters. That was the gravitational potential energy, mgh, and the potential energy of the spring, which is 1/2 kx squared. All right? So we're dealing with springs now. The potential energy is equal to 1/2 kx squared. Remember, the mechanical energy is the sum of the kinetic plus the potential energies. That's how we defined it. So for the mass spring system, E is going to equal to 1/2 mv squared, that's the kinetic energy, and plus 1/2 kx squared, and that's the potential energy. Remember, 1/2 mv squared, 1/2 the mass times the speed squared. Now, assuming there's no friction or drag or any kind of dissipative forces on the system, this energy will be constant throughout the motion. It will be conserved. Now, if the mass is at the limits of its motion, then what that means is that the mass is turning around and going back the other way at the extrema. At that point where it's turning around and going the other way, for just a split second, the velocity has to go to 0 at that point. Okay? What that means is that the kinetic energy is also 0 at that point, which means all of the energy is due to the potential energy of the spring. So at that point, we can say that the potential energy is 1/2 kx squared. We know what x is at the extrema. It's the amplitude of oscillation, A. So we can find the energy of the system, 1/2 ka squared. And that is going to be the amount of energy that it has as it goes throughout its motion. Now, at x equal to 0, the equilibrium point, x is equal to 0, so 1/2 kx squared is also equal to 0, so the potential energy is 0 at the equilibrium point. That means that all of the energy at that point is kinetic, so the maximum kinetic energy will be at the equilibrium point, the maximum potential energy will be at the extrema, and the kinetic energy will be 0 at those points. Okay. Setting 1/2 ka squared, which is the constant energy, equal to 1/2 mv squared plus 1/2 kx squared, you can see that as one gains energy, say the potential energy gains energy, the kinetic energy loses it, but the total energy remains constant, and they just exchange that energy back and forth. Let me show you that in an active figure, okay? So let me reset this, and then what I've done here is given this thing a push, and it's at the right, ready to be released from rest. Because it's at its maximum extension at this point, okay, and it's released from rest at that point, then all of the energy, as you can see here in this little bar graph, the total energy is in red, and the potential energy is in kind of that yellowy orange color. At that point, all of the energy is potential and none of it's kinetic. Now what's going to be plotted on these graphs are the kinetic and the potential energies. So let me give it a push and let's start, and you can see that what happens is as the potential goes down, the kinetic goes up, and vice versa, but the total stays the same all the time. Now the potential energy is 1/2 kx squared. It's kind of a parabola, and the kinetic energy is 1/2 mv squared, and it goes at its maximum value where the potential energy is at its minimum value. The kinetic energy looks like a little reverse parabola, okay? So you can see how that goes. You feel free to play with this on your own time. Okay, now you can solve using this 1/2 mv squared plus 1/2 kx squared equals 1/2 ka squared. You can solve that equation for v. Okay, and then you can find what the speed is as a function of the position. It's given by this expression here. V is equal to plus or minus V max times the square root of 1 minus x squared over a squared. V max is the maximum speed, and that's the speed at the equilibrium point where x is equal to 0. And the V max squared is k over m times a squared. Let me do another example problem for you talking about conservation of energy and these maximum speeds. So a 0.5 kilogram cart is connected to a light spring with a force constant of 20 newtons per meter, and it oscillates on a horizontal air track. That basically means that it's resting on a cushion of air so you can neglect friction. So calculate the total energy of the system and the max speed of the cart if the amplitude of motion is 3 centimeters. And then what's the velocity of the cart when the position is 2 centimeters? Compute the kinetic and the potential energies of the system at x equals to 2 centimeters. All right, so it seems like a lot. We're going to break it into steps. So first of all, the energy of the system, and that'll be the amount that's constant, is equal to 1/2 ka squared. All right? A is the amplitude, not the position at any point, any random time t, but at the extrema. So that's 1/2 ka squared, 1/2 times 20 newtons per meter times 0.03 meters quantity squared. When you solve for that, then you get 0.009 joules, or 9 millijoules. So that's the amount of energy that it has all the time. Now, the maximum speed is given by the square root of k over m times the amplitude a. When I plug in for that, my amplitude is 0.03 meters, and then times the square root of 20 newtons per meter divided by 0.5 kilograms gives me 0.19 meters per second. And all of these things, I'm not going to keep more than 2 significant figures in my answer. Every once in a while, that'll cause a little truncation issue, but bear with me. Now, if I want to solve for the speed at a different point, all I have to know is the x position. So v is equal to v max times the square root of 1 minus x squared over a squared. That was the equation that we showed on a previous slide. Plugging in for our numbers, we get 0.19 meters per second for v max. And now it asked about the position at 2 centimeters. So plugging in for that, the square root of 1 minus 0.02 meters squared divided by 0.03 meters squared gives me a speed of 0.14 meters per second, keeping 2 sig figs. It also asked, finally, for the kinetic and the potential energies. The kinetic energy is 1/2 mv squared. Plugging in our numbers, we get 1/2 times 0.5 kilograms times 0.14 meters per second squared. If I solve for that, I get 4.9 millijoules, again keeping 2 sig figs. The potential energy is 1/2 kx squared. That's 1/2 times 20 newtons per meter times 0.02 meters squared, and that gives me 4 millijoules. And you can see that with some rounding issues, we have 4 plus 4.9, it gives me 8.9, which is basically 9 millijoules for the system at this off-center position. Okay, so the energy is constant even though it's exchanged back and forth all the time between the kinetic and the potential energies. Another thing covered in these early sections in your textbook is the idea that an object going through circular motion, you can make an analogy between that and a mass on a spring going through simple harmonic motion. So what we're going to do is look at the projection onto the x-axis of an object that moves in a circle of radius a at some constant speed. Okay, so I have a little active figure which does that for us here. So what I can do, I'm going to speed this up a little bit and start it. And you can see here that I have this object that's going in a vertical circle, and there's a little light source shining down from the top. And what I want you to look at is the shadow of that circle moving on the bottom. And you can see that it looks just like a mass on a spring when you look at the shadow. Okay? So that's all they're saying. They're just saying that if you look in only one dimension, that the circular motion looks just like simple harmonic motion. And there's parallels that can be made in the equations between simple harmonic motion and circular motion. Again, that'll be posted online and you can play with it if you want to. So what we can say is that the x component of that velocity, in other words, the velocity of the shadow as it moves back and forth on the projection, looks just like the expression for the velocity of a simple harmonic oscillator. And so there's a lot of analogies that can be made there. Now finally, we know that the acceleration is equal to minus k over m times our displacement x. And we know that x is equal to a cosine omega t. So that means that my acceleration has to be also proportional to a cosine function. And in fact it is. The acceleration is minus a max times cosine of 2 pi t over r period. And a max is equal to k over a times m. So you can see that the acceleration and the position are both cosine functions. The constants that are out front multiplying the cosine function are different, but the cosine function itself is the same. Now, because we had that equation, v is equal to v max times the square root of 1 minus x squared over a squared, and x, of course, is going to be a cosine function, then you can tell from that little relationship that your velocity is also going to be sinusoidal. All right? It's not a cosine function. In this case, it's a sine function once you go through the derivation, but it's still a sinusoidal function. So, in fact, v is equal to minus v max times the sine of omega t, okay? And v max, of course, is a times the square root of k over m. So, in simple harmonic motion, your position, your velocity, and your acceleration are all sinusoidal functions. All right? Okay, that wraps up this lecture, and I'll see you in class.